Thanks, Dan. So this is the second in the 6-week Nobel series, so we're in the 6th year of doing this. And there are patterns that emerge, and I'll try to identify some of those. But I also have my own responses to what's happened in the last 6 years, which mold my thinking quite a bit. So it's always good to start out with some perspective, and I really like this picture because this identifies the large black hole. It doesn't look black because it's bright white. Why is it bright white and not black? Because it's surrounded by a gazillion stars and bright radiation from the corona of the black holes. And we'll talk about that a little bit more. But the reason why I like this is it's jam-packed with stars and therefore solar systems. And there are probably 100 to 200 billion of these solar systems in the Milky Way, and at least 1 trillion plus galaxies. So if you think we're special, we're not. And so that's a good piece of perspective to have. We're one species on one little planet in one corner of one galaxy. That's it. So one of the things that I pushed a little last week, and I'm going to push a little bit more this week, is that, there are all kinds of creation stories. One of the most moving time for me was, 10 years ago, coming back from Thunder Bay Clinic, and the BBC had a series on creation stories, and I caught it on the QEW, and it was so interesting, I pulled off and stopped the car and listened to it. But it was wonderful because, you can't say a lot in an hour, but they certainly covered the span of creation stories and the similarities, the similar themes that run in them. Well, science creates its creation stories, an abundant creation stories, its own take on creation. And this is just a meager list that came up with when I was putting this slide together. But the quantum universe, which we're going to talk about today, meaning the atomic, subatomic universe that we can't see, unlike that picture that I just showed you where you can see. That's the giant universe that we can see. The Big Bang and the expanding universe, the creation of life cycle of stars. I've told you before, I think last week, that our sun is the 3rd generation sun in our neighborhood of the Milky Way. So, and I just saw another article in Nature the other day about a planetary system like ours, but it's dying out. It's ended up in kind of a white star, primarily made up of helium. It lost all of its hydrogen, and the planets around it have disintegrated. Most of them have. So that's in our future. We know that's in our future from watching that cycle happen elsewhere in the universe. So that's what's coming. The creation of life cycles of black holes, we're beginning to understand that a lot better. The creation of the elements, beautifully worked out. And selected things, how land masses came to be and how they actually change. We know that continents form and then they break apart and reform. And been at least 7 or 8 such cycles since those cycles began on Earth. The beginnings, evolution, and relatedness of life. Isn't it remarkable that the same 4 bases that form the crux of DNA are the same through all life? Isn't that really? It doesn't matter what the life is. It's the same 4 letters. So it's a universal biological language. So we're related to all kinds of awkward things and gucky things and various other things we don't even know about because we share the same life molecules in many cases. Human evolution, that's a whole other thing that has to do with the human obsession with ourselves as a species. We are the most important species, so therefore we examine ourselves a lot. And we saw a bit of that last week with Pablo's stuff and looking at ancient DNA. Well, he wasn't looking at octopuses. He was looking at ancient humans or archaic humans. The evolution of the brain, that's a whole other story. Now you realize when I list all of these things, they're all interrelated, they're all part of a grander story. And science keeps adding bits and pieces like a huge jigsaw puzzle. And more and more pieces get added into it. So today is part of that puzzle and how that worked out. So, but it's always instructive to kind of go backwards. And I'll tell you, when we started this Nobel series, this was my favorite prize in that first year, 2017. They had just shown or demonstrated gravitational waves in 2 years before that. It's got to be a record. 2 years later, you get a Nobel Prize for it. That even beat Jennifer Doudna. I'm illustrating this for reasons. Number one, look at the ages when they got them. So you better hope that you live to get the award. The other thing about us, and some of you who know me know it, this is the question that I ask myself, when did the most creative stuff happen? I mean, when's the sweet spot, cognitively speaking, for humans to be creative, most creative? Well, it isn't in the 70s and 80s. And it's probably very similar to the sweet spot for physical activity, somewhere in those late teens, think Einstein here, and runs through maybe to the late 30s and 40s. Now, there's no doubt that we remain kind of vibrant and creative, but the really exceptional stuff tends to happen in those decades, kind of late teens through to early 40s, for most people. And I know that the literature people will argue with me about creative writing, et cetera, et cetera. We'll get into that eventually. But so they were interested in proving Einstein's hypothesis that when two heavy masses collide, if they do collide, they create, it's like throwing a big stone into a puddle, they create waves, like in a puddle, except that these are waves in space-time. And the other thing, it was a 3-decade engineering and managerial tribe. It's hard to imagine such an exercise these days in the United States, to be able to get secure funding for a project over multiple presidents and Congresses, support for a project. That's a remarkable thing. So that's one of the lessons that I took away from that. There, the gentleman, actually saw a picture of Kip Thorne the other day, so he's still alive. Here's the collision of two black holes. Now, this is an artist's rendition of this, but we actually have pictures of it. And a collision of two neutron stars. Neutron stars are the densest objects in the universe. And the little neutrons, you can jam them all together because they don't repel one another. And been likened to if you, for example, took the entire mass of the sun and crunched it into something the size of Manhattan. You get some idea of how dense it is. And so they create a lot of energy and gravitational waves or ripples in space-time when they collide. So that was a great Nobel Prize. I'm not going to show you how they did it, but now here's a Canadian story, because it's the next year. And let's just single out Donna Strickland at the University of Waterloo. What did she do? What was Donna's bright idea? Remember, she did this stuff as a PhD student. She didn't have her PhD yet. And she was working with lasers and at the limit of lasers. And she was trying to develop a high energy, high frequency laser. Well, it's very difficult when you have a high frequency laser beyond a certain limit to increase its power. And her bright idea, I'm not sure whether it was her or a mentor or several other people, but whatever, what they did is they took the high frequency laser beam, stretched it out, and then boosted its amplitude, and then crunched it back together again. I mean, it sounds so simple, But that's what she got her PhD for. It's what she got a Nobel Prize for. Put into a couple of sentences. So she did a great job. I don't know what she's doing these days at Waterloo, but that was certainly a great idea. This was a favorite of mine in 2019 because, physics is the only discipline in the sciences that has a well-developed theoretical side. I mean, if you take the Einsteinian minimalist approach, give me a desk, a pencil, and paper. That's it. I don't need any equipment. Those are that's never quite that pure. But James Peebles was a theoretical physicist who really gave us our common understanding of what happened to the universe from the Big Bang on, say, through to the first billion years after creation, if you like. And he provided a theoretical basis for thinking. We'll get into that a little bit later. And often they'll couple in a single Nobel Prize in physics that work with experimentalists, and that's what happened with Michael Mayer and Didier Queloz, because they discovered the first exoplanet. Well, now we know there are many thousands of exoplanets. There are almost certainly a million or more just within the Milky Way. We just haven't found them yet. So, in other words, places where there could be life. So the probability of life elsewhere in the universe has gone up exponentially just in the last 10 to 20 years for sure. So,
question?
Yeah.
So, we live on a planet. What's an exoplanet?
Oh, it's a planet that it's in the kind of the right space. I mean, it has liquid water, or at least it has water. It has the chemicals that could support life. They're usually rocky planets. Could support, and what we really mean here usually is life like us at some point. But they're really common in the universe.
Thank you.
Yeah, so that's fine. Now, here's the next year. This is a great year because the two experimentalists, Andrea Ghez and Reinhard Genzel, US, Germany, doing the same thing, trying to identify a black hole at the center of the Milky Way. And they competed with one another. Fortunately, their data supported one another. So that's why they're sharing the prize. And then we have a theoretical physicist, Roger Penrose at Oxford, who works with his head without any experimental stuff. And he showed that, I'll just take a quote from the Nobel Committee for the discovery that black hole formation is a robust prediction of the general theory of relativity. That's a big deal. Ever since Albert Einstein proposed or put forward his general relativity theory, there have been many attempts to kind of knock it, find some flaw in it. And every time it stood up. So there's a building problem here, because I'm going to talk about quantum physics. And quantum physics doesn't get along with general relativity. So there has to be something common between the two, linking the two. Okay, so just moving on from that year. And this is last year. This is big focus. Now, things have really changed in a year, haven't they? We didn't have the Ukraine war a year ago, and people thought the target of 1.5 degrees centigrade would be a reasonable thing. I think that's probably going to be blasted out of, I don't know where that's going to be, but it isn't going to be 1.5 degrees centigrade. And on the age issue, Sakura Manami did his work in the 1960s, Hasselmann in the 1970s, and Giorgio Parisi, who's the theoretical physicist here. These are the modelers here. this is a theoretical physicist and mathematician. And he was really bringing together that interplay between chaos and disorder and regular rhythms that characterize weather and climate. Okay, so interesting stuff last year. And the Nobel Committee went out of their way to support that these three persons and the climate change initiative. I mean, they made it very clear that the science supported that we were in trouble with climate change. Well, now they're meeting in Egypt, and I have a feeling not much is going to come out of that because everyone's preoccupied with Ukraine and other places, but certainly Ukraine. The world is not getting along well these days. And so that was last year in weather. Well, here's the one, if you had to pick one slide that illustrates climate change, this is it. Look at the long scale here. This is the last glacial maximum, the Ice Age. And when was that? 20,000, 15,000 years ago. Okay, we know that in Niagara. We were all under ice here. And then we're in the interglacial period, this long interglacial period here. There will be a return to this. I mean, global warming isn't going to continue forever. We will enter another glacial period for sure. But look at the spike at the end in that kind of last 100 years, especially in the years since the end of World War II. Because there's the chart. This is really the mean average surface global temperature in degrees centigrade. And it's really, I mean, these are standard deviations here, a couple of standard deviations. So that, not much change. And then you get this huge spike at the end. It's that spike that we're concerned about. Okay, so, and now to this year. Well, here they are, Elaine Aspect, 79, John Closer, 75, John Closer, 79, and Anton Zillinger, 77. All of these men did their, Closer did his stuff in the 1970s, 1980s, 1990s. So a long time ago, at least in my time frame. But there's a story here. Well, I like this picture. Those cartoons that the Nobel Committee are responsible for, I prefer these kind of photographs. They actually look pretty good. So let's just get into the quantum universe. I like this quote here. Abraham Pais, the best of the chroniclers of 20th century physics, remarked that quantum mechanics is like Vladimir Horowitz's assessment of Mozart's music. Too easy for beginners and too hard for experts. He meant that with a superficial grasp of quantum mechanics, one can make calculations, play the notes, so to speak, but to reach a full understanding of what the calculations mean, like Horowitz's mastery of Mozart, is a far more difficult task. That's certainly my sense of what goes on with quantum physics. So we're going to spend a few minutes just talking about how bizarre it is. So getting rid of all the stuff that I didn't actually need. There's the climate stuff. Here we are. Okay. So, well, entanglement at a distance. I'll tell you, in London Health Sciences, the Canadians of a certain age, meaning 70s and 80s, regularly headed off down to Florida. So I had to do the last I would see them for 3 or 4 months. And some of them, they've been married for 50 years or more, and they're really close friends and partners, sometimes spouses. And sometimes when a couple are really close, they actually behave, sometimes even look like they're the same. And one interesting phenomenon that sometimes they will mention is they might be at a social group and in a group and separate from one another, but somehow know what the other one is thinking. Particularly if they see them kind of talking to somebody and they kind of think they kind of know what their spouse or their friend is probably thinking. And it doesn't happen all that often, but it does happen. And but for physicists, entanglement is all about two or more particles behaving as one. So if these are the two fingers and I have two states, down and up, if I look at this, I'm going to repeat some of these things here, but before I look at a particle, I don't know whether it's up or down. I have to look at it to find out whether it's up or down. If the particles are entangled and I look at this one and it turns out to be up, the other one will go up instantly. Or down, sometimes the opposite, but responds instantly to whatever happened to this particle. Okay? Sometimes you can have 3, 4, 5, 6, 7, 8 particles entangled or locked to one another. Now, if you think about this, it's really strange. I mean, this is subatomic stuff. You can't visualize inside the atom. Just last year, in a very fuzzy picture, there was a picture of an atom, but certainly not electrons, and certainly not the nucleus of so this is kind of a weird world where you can't actually see what's there. And therefore hard to judge the behavior of what those particles, what they're actually doing. So this year's physics prize is about entanglement and quantum computers. Well, I'll tell you, if there were quantum computers on the horizon here, there wouldn't be any Nobel Prize for this. That's the importance of this stuff. It's not because they actually showed entanglement or provided evidence for such entanglement. I mean, that's an interesting academic exercise. But the practical point is that people are on the verge of creating viable quantum computers that are far more powerful than the computers that we have and handle much more data, or the potential to handle much more data. So, let's see. But there's another thing in all of this. The grand story for me in all of this, it's has to do with the struggle about the nature of quantum mechanics. And there are two actors on the stage. One is Albert Einstein, and the other one is Niels Bohr. They are very close friends. They get along with one another. They endlessly talk to one another. They get on trams without knowing where they're going, just so that they can talk to one another. But they argue a lot. And Einstein just can't apply quantum physics, despite the fact that he and Niels Bohr were the fathers of quantum mechanics. I mean, Einstein got a Nobel Prize for the quantum nature of light. That work was done in 1905. Niels Bohr several years later. So both men, intellectually very, very competent. Niels Bohr is kind of more comfortable with mystery than Einstein. Einstein really wants to see the concrete evidence. Well, it's very hard to get concrete evidence on stuff that you can't see. Okay? And where the world is really one of probability, but not certainty. So, just go on. So in this, this is a little bit of background, so just so you get a sense of who some of the players were. In 1900, just so, I mean, this is the Camelot period, this 1900 to 1930, but it embraces this quantum revolution in physics. And I can say that Max Planck, who I greatly admire, very conservative, I think I mentioned last week, very conservative scientist in the best German tradition, was looking at black body radiation. And he couldn't make the equations work. He was really, in his heart, in his head, this whole idea of a quantum nature of light, he just couldn't buy it. He was still stuck in the last century. And yet, to solve these equations for black body radiation, he took, he said, okay, I don't really believe in this stuff, but let me try it. Well, lo and behold, the equations work. And he actually, when he first presented this stuff to a group in Berlin, he apologized for using this quantum approach. Well, no such hesitation on the part of Einstein with this. Different age, different way of doing things. And so, I mean, he not only established the quantum nature of light, but all energy, including all the energy in black body radiation. So he was able to generalize beyond the quantum nature of light. I mean, that was his great vision. And we're talking about a guy in his late teens, early 20s now, working at the patent office. He's not, doesn't have his PhD yet. He's not working in a university. This is one really bright cookie. And he's unfettered by other people's opinions. He's bold, he's gutsy. Max Planck is cautious. Now, interestingly enough, Einstein's greatest triumph, general relativity, he did not get a Nobel Prize for. I mean, that's got to be one of the biggest faults of the Nobel system to oversee. Well, we can talk about that later. But just to show you how creative Einstein was, in 1905, here he is. As I say, he's not a professor, doesn't have his PhD, not working for a university, and he comes up with E equals mc squared. That has got to be one of the simplest, most profound equation in physics, because it directly relates energy to mass. It's obvious that mass and energy are interchangeable. That's the equation that explains the power of nuclear energy, the atomic bomb, not the H bomb, but certainly the atomic bomb. Because you only need to convert a tiny little bit of mass, and you get an enormous amount of energy released. This is the power of the sun here. Okay, you fuse hydrogen nuclei, you lose a little bit of mass in the process, a tiny little bit, and you get an enormous release of photons of energy. And so this is the energy of the sun. So that's one thing he does. Then he comes along with Brownian notion. It's like putting seeds on top of water, and if you wash them and warm the glass, you see these things kind of move around on the surface. Well, he's a very curious guy. This has been described the century before by Brown, no relative. And Einstein figures out, well, this has to be, without any direct experimental evidence, I'd say, this must be this random motion related to thousands, if not millions, of molecules, sometimes ganging up and pushing more in one direction than another, and that's why they're kind of jostling around. It's a great insight, and it was actually one of the best pieces of evidence for the atom. Well, Niels Bohr, he was very, he's an interesting guy in his own right. The first to tackle the arrangement of electrons about the nucleus. Well, he visited Rutherford in England, a very bombastic, very bright guy, but it's amazing that the two men hit it off so well, but they did. And Rutherford had worked out the proton, the center of the nucleus. And but as far as electrons went, he kind of thought of it as kind of a higgledy-piggledy arrangement anyway. He just wasn't vested and even thinking about it. But Bohr came along and said to you that, they're probably in some orbits, secluded in certain orbits that are related to energy. So Bohr posited that electrons were confined to specific quantal orbits. I kind of like this analogy. Likened by some to a theater. You go into the theater, you have a first row, second row, third row, fourth row, so on. Think of these orbits as quantal increases in energy. Or if you were climbing the steps up to the third and fourth row, it takes more energy to get to the fourth row than to seat yourself in the first row, right? So it's not a bad analogy. And so he established, or got it going, with this quantal nature of the orbits of electrons. I'm never quite sure whether it was Niels Bohr, or, he worked so collegially with people that it's hard to know whether it was a group idea or not. But anyway, now the next, I'm not going to say much about this, but we are in this period of quantum physics. This Camelot period, this magical 30 years, add another 10 years if you like, but mostly the first 30 years. If you think about what was actually accomplished in that period, the reality and nature of atoms was revealed by theoretical physicists, and those are all their names. Every single one of these people got a Nobel Prize. In fact, everyone up there got a Nobel Prize. This was a hot period in science. No doubt about it. The whole body of which work led to the creation of a brand new field, quantum physics, or some people prefer to say quantum mechanics, which was governed by, and this was the thing, this was the rub for Einstein, by counterintuitive rules such as Heisenberg's uncertainty principle. That really rubbed Einstein the wrong way. And I'll just say more about that because it's one of the central features of quantum physics. And the other one is the whole idea of entanglement of a disk and a distance. How does that happen? What are you saying is actually going on there? Although Einstein was one of the founding fathers of quantum mechanics, he didn't like that indeterminacy and chanciness that seemingly was at the heart of quantum mechanics. And something about this Heisenberg's uncertainty principle here. In 1927, Heisenberg really turned the world upside down. It happened, he had an allergy, a really bad allergy, and Niels Bohr sent him off to disappear into the bush and where there's good air and just get some rest. And he had something happen. He really thought about this a lot, and he came up with equations that explained this pure quantum mechanics, but also this uncertainty principle. And what does it say? It says, well, I alluded to it earlier. If we go back to if this is a particle, and this is up and that's down, before I look at it, I don't know what it is. I don't know what its state is. It's a big question. But when I look at it, it might be down or it might be up. I have no way of knowing which it is. That's an uncertainty principle. I don't know until I look. Now, isn't that a bizarre thing? I don't know. Is the looking created the change? It's just looking at it somehow changing some parameter of a particle. So now this pulls it together because Heisenberg, it's not as crazy as it sounds. A few moments ago I said the quantum world you cannot see. We have no tools for seeing an electron. or a proton, or a neutron, or their component parts. We simply don't have those tools. But he imagined creating a telescope, or at least a microscope, to do it. And what would you need? Well, electrons are really, really tiny. Now, in an ordinary light microscope, for you to actually see through the lens something, the resolution, the size is limited that you can resolve because of light. So if you're going to resolve something much, much smaller, you need wavelengths that are much shorter than visible light. In fact, so short that you're actually dealing now with gamma waves. And the problem with gamma waves is they're very energetic. So they'll actually blast the electron out of place or even destroy the atom. So the tool for this imaginary tool for observing electrons or seeing the nucleus components is really impossible. It's physically impossible to develop a tool to actually see them. You cannot do it without interfering with it. So observation does change the observed, and it makes sense. That's plausible. It's not as crazy as it sounds. And so now a little bit more on the nature of quantum physics. Now, some have already mentioned this, but photons of light and electrons, they have both waveform properties and particle properties. They can be both, and both at the same time. When two particles become entangled, now I mentioned this before, with one another, the properties of the combination dictates the behavior of both particles. So there's a common, almost, relationship. The individuality of the two particles that are entangled is almost lost in the common bond of the two, right? Does that make sense? The other thing is that information can be teleported. Now this was an interesting thing because how, if you do this, go back to this experiment, or let's say I send, as Klutzer, or first Nobel laureate today, if you take hundreds of entangled pairs of, say, photons of light, and you send them off in opposite directions, right? How is it that those two remain entangled? How does that work? Does that mean they could be light years apart and still entangled? And how could it possibly be that if you change one, the other instantly changes light years away? That's breaking the speed of light. That doesn't make sense. So anyway, this is kind of weird stuff. But it pays off because, let's see. Now this I rather like, the true Jacob. Einstein, he was a very good student of the Hebrew Bible, very well trained in the Hebrew Bible, so he often used language, God, and in this case refers to Jacob, and the H one, that would be God. So this is in his own words when he's saying about quantum mechanics. Einstein could never accept the absolute necessity of quantum mechanical indeterminacy. And to quote Einstein, quantum mechanics is very worthy of record. He did not deny the predictive value of quantum mechanics. He wasn't blind to this. He understood that it worked. But he has this inner voice, and which kind of drove him through his career. It tells me that this is not the true Jacob. The biblical reference, of course, here is to Jacob, who kind of fooled his father into getting the blessing. instead of his older brother. And so when he says, not the true Jacob, you understand what the illusion is about. And then goes on to say, the theory yields much, but it hardly brings us close to the secrets of the ancient one. In any case, I am convinced that he does not play dice. I mean, that quote is all over the common literature with Einstein. Just on that moment, I mean, Einstein often spoke of God, but never in the sense that God was personally involved in anyone's life or could change your fate. But anyway, it's an interesting illusion. So over many years, now imagine these two, they're very good friends, and they get into this, for them, very consequential argument about the nature of quantum mechanics. Was it a true reflection of reality or not? The quantum world has moved past it. They're already using it. In the 1930s, late 1920s, 1930s, Germany, Japan, United States, United Kingdom, France, nuclear physics was moving on. They were all thinking about something like an atom bomb, or at least that possibility. So theoretically, if not practically, they recognize the precision with which the equations of quantum mechanics predict results. Incredibly precise. So it works. So they kind of disengage from this argument between Bohr and Einstein. Einstein, with Hitler's ascension in Germany, he leaves Germany in 1933, ends up in Princeton, literally forgotten by the world of quantum mechanics. They moved on past him. He's kind of an old man. The two men get together from time to time. They are friends, and they have these discussions. But they're, as one person who was along with them at Princeton one time said, they talk past one another. They're not really listening to one another about what's going on. So they have these debates, and Einstein's a very bright guy. He develops a series of thought experiments as challenges to quantum mechanics. And one after the other, after several weeks, or in some cases several months, they figure out what's wrong with Einstein's thought experiment, as they kind of take a sigh of relief. Oh, God, beat that one. But they did not beat this challenge. Both men died with this question unresolved. Einstein first, and within a few years, Niels Bohr. So, and interestingly enough, in Niels Bohr's office, his private office, what did they find on the blackboard? But his take on Einstein's criticism of quantum mechanics, the last puzzle, unresolved. It's interesting. So let's move on to entanglement at a distance. Now, so there's the setting. The last puzzle he presents is 1935 with two students. And he claims that quantum mechanics was an incomplete theory by pointing out that quantum rules just don't make sense. That entanglement doesn't work. And it just doesn't make sense to Einstein. And as he said, he characterized it as spooky at a distance. Yeah. And what were his objections? Well, they came down to two. It violated Heisenberg's uncertainty principle. How could you have one particle over here and you change it and it always affects this one? When the uncertainty principle says you can't change this until you look at it. Follow that? Okay. And instantaneous means breaking the speed of light. By the way, they haven't solved that one yet. So now, an interesting fellow, Bill, he's an Irish physicist working at CERN. In his spare time, about 30 years later, he's aware of this. He's actually very sympathetic to Einstein. He thinks Einstein's on the right track, that there's some kind of something that quantum mechanics hasn't looked at. And so he develops a theorem and even some suggestions about practical experiments that might be carried out, that if they were carried out, would resolve this problem. And that now sits for another period of time. So this is 1935, and then up to 35, 45, in the early 60s. And Closer is going through the library at Columbia, where it's actually a real library with paper, books, and journals that you can rummage through. And he discovers Bell's theorem and his suggestion for an experiment. And he writes a letter to him. He says, "Has anyone else ever taken you up on this?" "No." "Well, would you do it?" And Closer was 29 at the time, the right age, and he took it on. And he showed that the results of his experiments were that it strongly supported quantum physics and not Einstein's claim that there were some hidden variables or variables in here that explained it. So there were some criticism of Closer's work on this, and so oh, by the way, I should actually show you, because this fits in with this. I don't know how many of you have been in labs, physics labs or chemistry labs. In a certain period, they all look like this. You know, there isn't a computer in sight there, at least as we would recognize it. Probably half the stuff is handmade or made in the lab. I certainly remember that the first time I was in Oxford, a lot of the equipment was actually made. You couldn't buy the stuff. And so this has all the hands of, this is engineering and science at the same time. You actually have to create the equipment to do the job. This is not off-the-shelf stuff. And that's what it looked like. I mean, that is so much looks like lab stuff in that period of the 60s and 70s and 80s. So that's, there was a catch in his discovery, which I won't get into, but then that's where Elaine Aspect came into it, because he thought, well, we can improve on this. We can make the experiments better. And he did. And it got even tighter. I noticed that just 2 weeks ago, there was a paper in Science of yet another embellishment of the thing to actually sew up the last leak in this and actually prove now that here we are in 2022, we now have airtight evidence that Einstein was wrong, finally. It's taken a long time. Anton Zeilinger, the other one here, he moved ahead, he moved the ball forward because he developed the first clear evidence of this teleporting, that data could be moved, quantum data could be moved from one quantum device to another. And to go on further, well, you have your computers, but well, maybe this is the time to talk about the computer side of it, because quantum computers, what's the advantage? In a digital computer, the kind of stuff that we have, our smartphone, if you've got a desktop or whatever it is at home. It's all kind of digital stuff, and it's the basic code is on or off. And the power of that computer is directly proportional to the number of bits, if you like. Each bit is on or off. Okay. Contrast that with a quantum computer. It's exponential. So it may be with one such particle could be 2. Take 2, it could be 4. Add another 2, it's 8, 60, 32, 64, 128, 256, 512, and so on. So it's exponentially more powerful. That's why it's potentially such an advance for something as complex as weather, where you have so much data and so much climate data and weather data that's overwhelming for most computers, except the very fastest ones. But quantum computers that's their stuff. It's their playground. The other thing about quantum computers is that you can't break into them. Because if you attempt to break into them, any information in there instantly disappears. It's gone. So it can break into our regular computers, and that's one of the hazards for Western security. If some other China or the United States or Iran or whatever it is, and by the way, they're all working on this, if they develop quantum computers to that point, they could break into even the most safely held regular computers, digital computers, systems, but not themselves be broken into. So they have advantages. What's the disadvantage? Well, to the security of this entanglement data, this quantum data, depends on the temperature. So the computers run at almost absolute zero, just above it. So you're not going to have a handheld device as a quantum computer. That isn't going to work. And so there's China's big thing. Now I can tell you China's big. Just look, I looked at for this Nobel Prize, if you look at the reference list for on quantum computing, probably a third of the references are Chinese. And several universities involved. And in some instances, some of the heads of those things were trained in the US or Europe, going back 10, 20 years ago. That's fair enough. I mean, that's the way things work. But what they devised, there are 2 quantum computers here, over 1,000 kilometers apart, teleporting between one another, and a satellite up here. So no one in the West has done anything like that, at least for that kind of distance yet. Yes?
Your reference says it was written in 1920?
No, that's 1920. That's 2020. 2020. Yeah, sorry about that. My quantum computer sometimes doesn't work. Yeah, so I'm glad to pick that up. Yeah, that's 2020. Yeah, don't scare me like that. Yeah, so now 2 things, just closing things about quantum physics and general relativity. Well, there are 2 places where they come together. One place is with the Big Bang, because in that first, the estimates would be, in that first trillionth of a trillionth of a trillionth of a second, it was a quantum world or universe at that time, driven by the Heisenberg principle of random kind of distribution. And then it expanded so rapidly in that period of time that out to the visible horizon at that time, or to limits of the universe at that time, the distribution of particles and energy and matter was all randomly distributed, like a quantum distribution. Okay? So for the very that first fraction of a second, the universe was quantum. It was dictated by quantum physics or quantum mechanics, to the best understanding. And then after that, general relativity didn't take over; they overlapped for a period of time. So, and this, I don't remember. You may remember this figure, maybe 10 years ago, a little more than 10 years ago. It was in every newspaper. And it's really the distribution of this cosmic background radiation that was released about 300,000 years after the Big Bang. Before that time, everything was so energetic and so hot that protons couldn't link up with electrons. It was highly ionized, and any quanta of light couldn't escape. After that time, the temperature had fallen to the point where actually they could link up with one another. And that first light, if you like, in the story, the science story, first light in the universe, 325,000 years after the Big Bang, the universe literally lit up temporarily. And the leftover of that is a tiny bit of radiation and temperature different. Now we're talking about a few degrees absolute temperature here, just above absolute zero. But these are the random variations. And a Harvard group thought that they were going to, because of this inflationary expansion of the universe within a trillionth of a trillionth of a trillionth of a second, they thought they were dead certain they were going to get a Nobel Prize for that. Unfortunately, the Max Planck Institute had another look at the data, and the data didn't hold up. So despite this party being organized for the celebration, they didn't get it. And Nature and Science had to print retractions. You don't often see that one. So that was interesting. But that's just this cosmic background radiation. And what about black holes? Well, you know that black holes, they have an event horizon. Stephen Hawking, probably remember that, but there's an edge here. And matter outside of it's kind of whirling around the black hole. It's hot, it's energetic, there's a lot of radiation, a lot of particles, stuff from stardust stuff from the breakup of stars and other bodies that got too close to the black hole. But they haven't fallen in. And when they fall in over that event horizon like Niagara Falls, even light can't escape the gravitational effect. So that's why the black hole. So general relativity, you just saw that I pointed out that predicted the birth and at least what you see in a black hole outside of it very well. But we haven't a clue what's actually going on inside a black hole. Some people think quantum physics rules there, but we don't know that at all. And some people talk about, well, what happens to information? Well, that's not textbook information, but you know, about the spin of a particle, the polarity of quantum light, all of those are certain quantities. And it all represents information. Well, what happens to that information that goes down the hole? And if the hole as Stephen Hawking suggested, black holes eventually die, not in an explosion, but they leak energy over time. And it dissipates. And can that information be reconstructed? I have no idea, not a clue. But those two, general relativity and quantum mechanics, those are the two places where they come together. One other one is this little conway, the wormhole in Star Trek. Talks about these, but it's actually a prediction of Einstein's general relativity, that you could have two areas, two sinkholes for gravitation, like a black hole, and they could communicate with one another through a wormhole, if you like. And there have been some movies. Now, this guy is from NASA, so he probably knows what he's talking about. But so this is his imagined idea of using it as a transport device, a quick dodge around the universe without having to take a gazillion years to get there. So that's an interesting thing. So we've covered a lot of stuff. Now, what is that? Well, 1990, Voyager. There were two Voyager satellites sent up, and they were sent to the far reaches of our solar system. And Voyager 1 was given a command to turn around and take a picture of Earth. That's Earth. That little dot. That tiny little dot. And as Carl Sagan said, where all history, all evolution, every book that's ever been written, every war that's ever been fought, every politician, everything that's ever happened on that dot that we know about. What you don't see in this picture is that this is kind of enhanced to bring Earth out. But in doing that, you can't see the huge number of other stars out there, or potentially other solar systems. So it's a remarkable perspective. I think it's an amazing thing using an old tool. By the way, they're still traveling, those two Voyagers. And if we went back to the original slide of the Milky Way, you'd realize that even after traveling 20, 25 years, they haven't gone very far in the Milky Way. They're still well within the Milky Way. Simply because of the huge distances involved and the limits of the speed of light you can't travel. So, I mean, it takes what? I have to look up to something again, but it takes about 20 or 30 generations to actually reach the center of the solar system from where we are traveling at light speed. Imagine 20 generations. 20 generations is back to Jesus' time, almost. So it's a long, long time, and certainly the original crew will not be the original crew there. And imagine the time coming back to report. And remember the speed of light. If you travel near the speed of light or anything like it, you age. Your clocks go slower. So you could go to the center of the universe or some long distance and come back and find out that your child is now, a grandparent, or maybe already deceased at that time, simply because of special relativity. And so that, all right. So what all of this does is, and we can stop here for sure. These are all stories. This is a remarkable story. It's a remarkable story about Niels Bohr and the relationship he had with Einstein. It's a story about how science kind of mumbled and but basically got it right finally. And but it's about a huge universe beyond our universe, but one also that's very, very different. That's absolutely tiny and we can't see. And it's a universe of probabilities. And that's all we can know about it, all we'll ever know about it. And the two actually work together, even if we can't make them fit together. So, and humans have been, I would think, speculating now, just based on alluded to it last week, based on intentional burials, based on some evidence of long-term care, based particularly on leaving markers, figurative art, is Neanderthal stuff, 60,000 years ago, 20,000 years before modern humans got to Western Europe. And figurative art, musical instruments, the first flute was a Neanderthal one. There it is. And then 30,000 years later, modern humans produce this really well-crafted ivory one, but 30,000 years later. So using these all as markers for the culture and the time of what people were. I mean, obviously, they created music, they enjoyed music, they enjoyed figurative art, they used it for whatever reasons, and they certainly speculated, I would think, about futures beyond the grave and about their ancestors. And so this is, and that's all within, say, the last 100,000 years that we know about. So all the stories that have ever been told are relatively recent. And they're very similar tales in some ways. It's when we get into the details that things kind of get muddy. So, so today was another one on science. So next week is chemistry, which will be shorter, I guarantee you. But it is superb. It's two of those laureates next week are just really outstanding. So that'd be good. So any questions or thoughts? Yeah, Jay.
Well, I have one technical question. Is entanglement something that can occur beyond pairs in multiples?
Yes. Yeah, I think I mentioned that once. You could have 3, 4, 5, 6, 7,
sorry,
8, yeah.
I didn't realize that.
And then it becomes more complex.
Yeah.
And it can carry an almost infinite amount. That's a dangerous word in science to use it for, but a lot of data, huge amount of data,
So,
in what's called a qubit.
yes,
QU
right.
bit.
Yes, you
Qubit.
put that up there, right.
And yeah,
So is that the way that they are sort of engineering their quantum computers? It's not just two communicating, but
no,
more?
the work. There are a couple of papers I had up there, but no, they in Europe now. I think it's Denmark, but there's one other center involved. Are working on developing a quantum internet.
Okay, that's what I thought. Yeah.
Yeah, quantum internet. But it's relevant. I mean, we're talking very early days
Yeah.
before kind of practical stuff comes along. This is kind of like 1890 before the Camelot years started.
Mm-hmm.
And the quantum world. That's how I see it. Yeah.
Yeah, I guess the most interesting slide was the one where you showed the Chinese computers. Had they developed the quantum computer and they are...
Oh, the Chinese one? Yes, yes. They claim so.
Okay. So
One of the lead author of one of the papers is a fellow from Beijing University, and he worked with one of the Nobel laureates. The 3 here. I think it was the only.
So they're going to raise the answer of us. I guess.
It's hard to read that. I mean, that was kind of a publicity stunt, I think. I don't think they were conveying important data.
Okay.
And probably would have had trouble spelling my name. Even Bill.
Yeah.
But in that they could send data.
To the satellite.
Yes, and back and between land stations over 1,000 kilometers apart. That's a big achievement. But then imagine where we came from the digital world.
Yeah.
You look at the computers at Harvard in the 1940s. Big, clunky things, that our smartphones so far ahead of them. So this is, again, I think a development, a very steep curve.
Mm-hmm.
Yeah.
So that, I mean, that, following on that pattern, because as you said, the early computers were huge.
Yeah,
Right.
absolutely
And
huge.
now
Very
now
huge, Sheila, for very little.
Yeah, and now we
accomplished.
but now we all have, you know, the micros.
Yeah.
Microsoft.
Yeah.
This would obviously apply to quantum computers.
Yes, I think so. I think so. Well, I don't know that they've solved that requirement for working at almost absolute zero. That would be a bugaboo, I think.
Well, now we were talking some years, but.
Yeah, I don't know. I can tell you what the pace of the publication pace is steep. And China, Iran, interesting, but that's a very well-educated population, Iran, especially in engineers. Ukraine was before the bloody war. And Russian engineers and certainly China and several centers in the United States. Oxford, I know, is heavily involved. I know that there are a couple of places in Denmark and Austria. I don't know, but I just know the literature. Just follow the literature.
Yeah.
The literature points to a lot of people getting involved at a very high level. Yeah.
Is there any relationship between the ancient measurement of qubit and what you say qubit is with regards to?
No, it's the little, it's the word that the quantum computer people have said to differentiate it from a bit.
Oh, qubit.
Standard, yeah, they just added Q at
Okay.
the start of bit. So
Okay.
that's qubit. Yeah,
Okay.
that's right.
Yeah. What is your thoughts with regards to, because I'm looking at a lot of these names, a lot of them are German. I'm thinking about the 20s, the 30s,
Yeah.
and then when Hitler came in, the Nazis, the development, it was just seemed like it was a hotbed of so much development in so many aspects of science, chemistry, physics.
Germany was incredibly productive in the latter third of the 1800s and right up to World War II and through World War II.
Right.
Because they got a lot of industrial support, a lot of support from the federal government, and places like the Max Planck and other places. The centers of what we would call excellence.
So was there
They were
education
developed
system?
in, say, 1880, 1890 in Germany, and very well supported.
Yeah, and it was actually superior to what was taking place, at least in the US. Oppenheimer, for his advanced degrees, went to Germany because there was
Right.
just not enough for him in the States. And then he
Yes.
brought it back, and then he really began to sort of help develop in Caltech, I think in California.
Very disciplined, well trained, like Pablo, like last week,
Oh.
with the ancient DNA story. I mean, the Max Planck, the very German kind of thing to take a hot area or what they see as a hot area and then fund it really well. And we do, or yes, we do that. U of T does it well. Not so much McGill anymore. And at least in the biological sciences, believe it or not, Calgary. But you know, if you look at who gets to be a professor in the United States, who gets tenure, it comes down to about 6 universities that create 80% of the tenured profs in the United States. So we're talking a very rich, dense, but in spikes, you know, across the country. I'm tempted to say before this election, a lot of dumbness and some real brilliance in the place. But that struck me, holy mackerel, 80% of the tenured profs came from 5 or 6 institutions in the United States.
Is it because they basically have more money?
Well, success breeds success, right? And they also get a lot of industrial support. And, you know, if you go to Harvard, every Harvard student is badgered for money the day he or she leaves.
Right.
I don't have any troubles with that kind of system. I think it's very good. I mean, I don't know where Harvard's funding is now, but I think it's over the 100 billion mark. I would guess U of T's lucky if it's $1 billion. Maybe it's a little more than that. But U of T, when I look at just from the science, we've got the arts and everything, I don't know about that, but on the science side, if I look at the, say, top 100, but especially the top 50, U of T is consistently there somewhere in the 40s. There are the predictable ones, like the Oxford and the Cambridge and the Harvard and the American Technical, Caltech, MIT, those kind of institutions. But the blur are the number of Chinese high-level institutions that have just come in. I mean, I can assure you that, say, 10 years ago, there wasn't one in the top 50. This year, there were 2 in the top 10, and Oxford and Cambridge were 11 and 12. So that'll give you some idea of the quality. Now, and these are international criteria. It's not China blowing its horn, you know, although there is that. But we do a pretty good job of that ourselves. But these are acknowledged international criteria, citation indices, who reads what, who gets what. It's interesting just this year, in the last week, no surprise, because that's Svante Pavlov's kind of stuff, it's European. But this time around, it's interesting looking at the rubber, and next week in chemistry, the number of, I mean, the Nobel committees that review this stuff, when they do they give press release, there's one to the public, and there's a scientific paper. If you go to the scientific paper, they don't give you 500 references. They give you 100 of the most important. And in even in this one, but next week in spades, the number of Chinese references, or for example, in science, they or at least in Science and Nature, they review the Nobel laureates in science. They went to a Chinese guy to review these things for him. And he had trained with one of them. There's a message in that. They've got a really good educational program. They know what they're doing, they have focus, they're in it for the long game.
A lot of people too.
Mm-hmm.
A lot of people too.
A lot of people, but they're in it, you know, this is very intentional planning. And obviously they're not rubbing the science community the wrong way, or they'd be disappearing.
Right.
They're not disappearing. And a fair number of Americans, I don't know about the UK or Europe, but a fair number of Americans have a chair, if they're top ranked, they get a chair in China at one institution. I mean, it's a good way of seeding something.
What do you mean by
See,
that? Sorry.
If it's a common enough thing. If somebody does something really well and it's recognized to be really well by the community, and they get particularly a Nobel Prize, there'll be a lot of places after them
I see.
to move, not to move their home and that kind of thing, but for an appointment there. And that happened with last week because Pablo had an appointment in Singapore. I'm sure he's not there very often, but he's very good to have somebody around there just feeding the place, where the youngsters can come along and those kind of easy conversations. Yeah.
Share the knowledge.
Yeah, sure, exactly. Develop that, you know, science depends on community. I mean, the freak is Einstein, kind of the oddball, but he's anything that represents the the usual thing. The usual thing is a community more like Neil's Board, where you're kind of a really engageable person. You like to talk, you like to be around people, other people who are talking. You like long walks, you like sailing trips in which you endlessly talk, and you form relationships. He had a very close relationship with Heisenberg. I mean, they're very different personalities, but Bohr was a very comfortable mentor to be with. Einstein didn't have any, he had lots of friends, but not, there aren't many papers of Einstein with one or two other people. Okay, all right, yeah, thanks.